Welcome to AQA GCSE Chemistry Topic 4 Revision Chemical Changes. Metal oxides. Metals react with oxygen to produce metal oxides. The reactions are called oxidation because the metals gain oxygen. The mass of the metal will increase because oxygen has been added. For example, iron plus oxygen will form iron oxide. The simple equation for this is 2 moles of Fe will react with 3 moles of oxygen to make 2 moles of iron 2 oxide. As I said, this is oxidation because oxygen has been added to the metal. Reactivity series. When metals react with other substances, the metal atoms form positive ions. For example, all group 1 elements have 1 electron in their outermost shell. To form a noble gas structure, that is a full outer shell, they lose their outermost electron and as a result become positively charged. Group 2 elements have 2 electrons in their outermost shell, and when they lose their 2 electrons to have a noble gas structure, they form positive 2 ions. Group 3 metals such as aluminium form positive 3 ions. And transition metals have variable charges. So for example, iron 3 has lost 3 of its electrons to form a 3 plus ion. But iron can also form a 2 plus ion in iron 2, and these are normally denoted in Roman numerals. Metals lose their outermost electrons to form positive ions. Therefore, all metals can undergo oxidation, as oxidation is loss of electrons. When non-metals react with other substances, normally metals, the non-metal atoms form negative ions. For example, group 6 elements, such as oxygen, has 6 electrons in its outermost shell, and to obtain a full outer shell, or noble gas structure, it has 2 electrons added to it, forming a negative 2 minus ion. The halogens, group 7, have 7 electrons in their outermost shell and gain an electron to form a negative 1 ion. Reduction is the opposite of oxidation. Therefore, reduction is the gain of electrons. We can remember the difference between oxidation and reduction by using a mnemonic called oil rig. Oxidation is the loss of electrons. Reduction is the gain of electrons. And therefore, we can use the mnemonic oil rig. Oxidation is the loss, OIL. Reduction is the gain, RIG, of electrons. The reactivity series. The reactivity of a metal is related to its tendency to form a positive ion. Metals can be arranged in order of their reactivity in the reactivity series. At the top of the reactivity series is potassium, and at the bottom, platinum. Potassium is the most reactive, platinum is the least reactive. Therefore, potassium has a greater tendency to form positive ions than platinum. The metals potassium, sodium, lithium, calcium, magnesium, zinc, iron and copper can be put in order of their reactivity from reactions with water and dilute acids. Non-metals, hydrogen and carbon, are included in the reactivity series, although they are not metals. More reactive metal can displace a less reactive metal from a compound. For example, magnesium and copper. Magnesium is higher in a reactivity series and therefore has a greater tendency to form ions than copper. If we react a solution of copper sulfate ions with magnesium metal, the magnesium will displace the copper from solution, forming copper metal, and the magnesium will form ions and go into the solution to form magnesium sulfate solution. Magnesium has a greater tendency to form a positive ion than copper, and therefore loses 2 electrons to form magnesium 2 plus ions. Magnesium has been oxidized, as oxidation is loss of electrons. The copper 2 plus ions in solution gain the 2 electrons that the magnesium has lost, forming copper metal. The copper ions have gained electrons from the magnesium and therefore have been reduced. The combined reaction is called a redox reaction. Extraction of metals and reduction. Unreactive metals, such as gold, are found in the earth as the metal itself, uncombined with oxygen. Most metals are found as compounds that require chemical reactions to extract the metal from the metal oxide. Metals less reactive than carbon can be extracted from their oxides by reacting with them with carbon, because carbon is more reactive than zinc, iron, tin and lead, and therefore will remove the oxygen from the metal oxide, producing the metal. Reduction involves the loss of oxygen. The reactivity of metals with water or dilute acids is related to the tendency of the metal to form a positive ion. Metals below hydrogen in the reactivity series do not react with dilute acids because hydrogen ions in solution will have a greater tendency to form the ion. Metals below calcium react very slowly with cold water because the metals below calcium have a weaker tendency to form positive ions than reacting it with water. You need to be able to write word and symbol equations with metals with water. For example, potassium plus water makes potassium hydroxide and hydrogen. The symbol equation for this is 2 moles of potassium, symbol K, reacts with 2 moles of water, H2O, to form 2 moles of potassium hydroxide and 1 mole of hydrogen gas. In this process, the potassium metal loses an electron to form potassium ions. Since the potassium has lost an electron, the potassium metal has been oxidized. Reactions of acids with metals. Metal plus acid forms salt and hydrogen. The mnemonic to remember this is MASH. For example, potassium plus hydrochloric acid will make potassium chloride and hydrogen. 2 moles of potassium and 2 moles of hydrochloric acid will form 2 moles of potassium chloride and 1 mole of hydrogen gas. In this reaction, the metal loses its outermost electron to form a positive ion and therefore has been oxidized, since oxidation is loss of electrons. Neutralisation of acids and salt production. The particular salt produced in any reaction between an acid and a base or alkali depends on the acid used. For example, hydrochloric acid produces chloride salts, nitric acid produces nitrate salts, and sulfuric acid produces sulfate salts. It also depends on the positive ion from the base, alkali or carbonate. A base is a substance that neutralises an acid. However, some bases are soluble in water. We call these alkalis, but some are not, and therefore they are called bases. Alkalis are soluble metal hydroxides. Bases are the remaining insoluble metal hydroxides. Also, acids are neutralised by metal oxides to produce salt and water, and also by metal carbonates to produce salt, water and carbon dioxide. Alkali plus acid forms water and salt. The acronym to remember this is ORS. For example, sodium hydroxide plus hydrochloric acid makes water and the salt sodium chloride. The hydrogen ion from the acid swaps places with the sodium ion from the alkali to form the salt and water. Base plus acid forms water and salt. The acronym for this is BORS. For example, Magnesium hydroxide is an insoluble metal hydroxide and therefore is called a base. It neutralises an acid to form water and magnesium sulfate. Again, the magnesium ion swaps places with the hydrogen ions of the sulfuric acid to form magnesium chloride, and the hydrogen ions react with the hydroxide ions to form water. Metal oxide plus acid makes water and salt. The acronym for this is MOAS. For example, copper oxide and nitric acid react to form water and copper nitrate. Again, the hydrogen ions from the acid and the copper ion from the metal oxide react together, swap positions to form the salt, copper nitrate and water. Lastly, we have metal carbonate plus acid makes water and salt. The acronym for this is McCaws. For example, calcium carbonate plus hydrochloric acid forms water and salt and carbon dioxide. Again, the hydrogen ions from the acid swap positions with the calcium ion to form calcium chloride, but in this case, the hydrogen ions and the carbonate ion react to form water and carbon dioxide. Required Practical 1. Making a soluble salt. Soluble salts can be made from acids by reacting them with insoluble substances such as metals, metal oxides, metal hydroxides or metal carbonates. In the example, we are going to make zinc sulfate by adding granulated zinc metal. We are warming the acid and adding the zinc a spatula at a time and stirring, and as it reacts the zinc will dissolve to form zinc sulfate and water. In this case, the dilute sulfuric acid is the limiting reagent, and at some point when we keep adding the zinc it will no longer dissolve because all of the acid has been used up. To remove the unwanted zinc, we have to filter the solution using a filter funnel and filter paper. The excess zinc is removed as the residue within the filter paper, and the filtrate, the solution, zinc sulfate, is left. This is then transferred to an evaporating dish where it is heated again to reduce the volume of water by half, and then allowed to evaporate on a window ledge so that zinc sulfate crystals can be formed. This process is called crystallization. The pH scale and neutralisation. Acids produce hydrogen ions in aqueous solution. Aqueous solutions of alkalis contain hydroxide ions. The pH scale ranges from 0 to 14 and is a measure of the acidity or alkalinity of a solution and can be measured using universal indicator or a pH probe. A solution with a pH of 7 is called neutral. Aqueous solutions of acid have pHs of less than 7 and aqueous solutions of alkalis have pHs of greater than 7. In neutralisation reactions between an acid and an alkali, hydrogen ions react with hydroxide ions to produce water. This reaction can be represented by the ionic equation. H plus OH forms water. As you'll notice, the anion of the acid, for example Cl- in hydrochloric, NO3- in nitric, and SO4- in sulfuric, is not represented. Nor is the metal ion from the alkali, for example Na+ in sodium hydroxide, or Mg in magnesium hydroxide, or even the sodium carbonate ion in sodium carbonate. This is because these are spectator ions, and the neutralisation reaction can be simplified by removing the spectator ions to form H+ plus OH- makes water. This means this ionic equation represents all neutralisation reactions. Universal indicator can be used to measure the approximate pH of a solution, where green is neutral, red, orange and yellow are acidic, and blue and violet are alkaline. For those students studying chemistry only, you also need to be able to describe how to perform a titration. To start off with, you want to use a conical flask and a burette. The conical flask will contain a sample which needs to be analysed. The burette contains a solution of a known concentration. The flask also contains an indicator such as phenolphthalein or methyl orange, which will change colour at the equivalence point called the end point. The solution of the known concentration of sodium hydroxide is added slowly to the sample. As the sodium hydroxide runs into the flask containing our acid, we notice that the indicator changes colour. As we swirl the flask though, and it comes into contact with more acid, the colour disappears, until we reach a point where the indicator remains the same colour. This is called the end point of the titration, and it approximates where there is an equal amount of hydrogen ions and hydroxide ions. You need to be able to calculate volumes or concentrations or the amount of an acid or an alkali in a titration. For example, in a titration where 25 centimeters cubed was titrated against HCl, we can put the equation into this table. As you're aware, we need to convert centimeters cubed into decimeters when carrying out concentration calculations, because the standard unit of concentration are moles per decimeter. So in the table I've put an extra row where we can do this. So first of all, I've divided the volume of sodium hydroxide by 1000 so that it equals 0.025 decimeters. I know the concentration of the sodium hydroxide as it was given to me in the experiment of 0.1. To calculate the amount of sodium hydroxide, I times the concentration C by the volume in decimeters cubed. So I get 0.1 times 0.025, which gives me an amount of 0.0025. And the equation shows that 1 mole of sodium hydroxide reacts with 1 mole of hydrochloric acid. So therefore at the end point I have the same amount of acid and alkali. Therefore I also have 0.0025 of hydrochloric acid. Now I know the volume and the amount, I can calculate the concentration, but I will need to change the volume into decimeters cubed. So the volume in decimeters cubed is 0.0301, and then to work out the concentration I can divide the amount 0.0025 by the volume in decimeters cubed 0.0301, and will give me the concentration of 0.0831. Strong and weak acids. A strong acid is completely ionised in aqueous solution, for example hydrochloric, nitric and sulfuric acids. In the diagram, the red ball represents the hydrogen ion and the purple ball represents the anion. For example, in hydrochloric acid it would be Cl- ions. As you can see, all of the acids have completely dissociated. A weak acid is where only partially ionised in aqueous solution, for example ethanoic, citric and carbonic acids. In the diagram you can see that only some of the hydrogen ions have dissociated from the acid. This represents a weak acid because they have only partially dissociated. For a given concentration of aqueous solution, the stronger the pH of the stronger the acid, the lower its pH. pH scale. As the pH increases by 1 unit, the concentration of the solution decreases by a factor of 10. This means that if a solution has a pH of 1 and another has a pH of 2, there is 10 times as many hydrogen ions in the pH solution of 1 than there is 2. Dilute and concentrated. A dilute solution has a small amount of solute dissolved in it, and so has a low concentration. A concentrated solution has a large amount of solute in the solvent, and so a high concentration. Many students confuse strong acids and weak acids with dilute and concentrated acids, but these are two different things. A strong acid, such as HCl, can be dilute or concentrated, depending on how much solvent there is compared to the acid. Electrolysis. When an ionic compound is melted or dissolved in water, the ions are free to move about within the solution or the liquid, and therefore can carry charge. These liquids and solutions are able to conduct electricity and called electrolytes. Passing electric current through electrolytes causes the ions within the electrolyte to move towards the electrode. Positive ions move towards the negative electrode called the cathode, and negative ions move to the positive electrode called the anode. Ions are discharged at electrodes producing elements. This process is called electrolysis. For example, when a simple ionic compound, e.g. lead bromide, is electrolyzed in the molten state using inert electrodes, the metal, lead, is produced at the cathode and the non-metal, bromine, is produced at the anode. Using electrolysis to extract metals. Metals can be extracted from molten compounds using electrolysis. Electrolysis is used if the metal is too reactive to be extracted by reduction with carbon, or if the metal reacts with carbon itself. Large amounts of energy are used in the extraction process to melt the compounds and to produce electrical current, so those metals less reactive than carbon are extracted with heating with carbon instead. Using electrolysis to extract aluminium. Aluminium is manufactured by the electrolysis of a molten mixture of aluminium oxide, its ore, and cryolite. Cryolite is added to the electrolyte to lower the melting point of the aluminium oxide and save energy, and therefore it is more cost effective and better for the environment. Graphite, an allotrope of carbon, is used at the positive electrode, which reacts with oxygen to make carbon dioxide, and so they must be continually replaced. The ions discharged when an aqueous solution is electrolyzed using inert electrodes depends on the relative reactivity of the elements involved. At the negative electrode, the cathode, hydrogen is produced if the metal is more reactive than hydrogen. At the positive electrode, the anode, oxygen is produced unless the solution contains halide ions and the halogen is produced. Required practical 3. Electrolysis of aqueous solutions. In the electrolysis of brine, sodium chloride solution, the ions present are sodium, chloride, and the hydrogen and hydroxide ions from the dissociation of water. At the negative electrode, hydrogen is produced as sodium is more reactive than hydrogen. Each hydrogen ion gains an electron to form the H2 molecule. At the positive electrode, oxygen is not produced because the solution contains chloride ions, and so chlorine is produced. Each chloride ion has an electron removed and the chlorine molecule, Cl2, is formed. The sodium and hydroxide ions remain in solution, and so sodium hydroxide solution is made. In the electrolysis of copper sulfate solution, the ions present are copper 2+, the sulfate ion SO4 2-, and of course the hydrogen ion and the hydroxide ion from the dissociation of water. At the negative electrode, copper metal is produced because it is less reactive than hydrogen. At the positive electrode, oxygen is produced because the solution does not contain halide ions. Representation of reactions at electrodes as half equations. At the cathode, the negative electrode, positively charged ions gain electrons, and so the reactions are reductions. For example, hydroxide ions are reduced to form oxygen, water, and lose 4 electrons. This is if a halide ion is not present. If a halide is present, the halide ion becomes reduced and becomes a diatomic halogen. At the anode, the positive electrode, negatively charged ions lose electrons, and so the reactions are oxidations. For example, hydrogen ions gain 2 electrons to form the H2 molecule if the metal is more reactive than hydrogen. Or, for example, copper 2+ will gain 2 electrons to form copper metal if the metal is less reactive than hydrogen.